The title of the course is Write Your Own Tiny Programming Systems, and the use of the word system here is deliberate. I intentionally didn't call it Write Your Own Tiny Implementation of a Programming Language, and I should explain why that's important. So programming languages is an idea that is well studied, and it's kind of based on the metaphor that programming is writing some code. So programming languages are these sort of linguistic entities, or programs are sort of things that are written. And when you look at programming language, you're just looking at the kind of syntax and semantics of the language. You can model these formally. You can talk about how you implement a compiler for a programming language that takes the source code and transforms it into an executable. You can think about the different programming paradigms that the constructs of the language enable, or what's the sort of type checking mechanism. But all the time we are thinking about some sort of language for describing programs. And this has a lot of implications around how you interact with the program. So programming languages is an established concept, and we know very well how to study this. But if you look at a lot of other interesting programming environments, very often the important thing is how you interact with the system. The system can be stateful. And what matters is not so much the kind of bits of code that might be embedded in the system, but how exactly it reacts, how it gives you feedback when you do something, what's the kind of interactive user interface. The two examples I have here on the screen are Smalltalk, and I will say more about that later, and HyperCard. And HyperCard was this end-user programming environment where people could easily construct little programs, and it had a lot of interesting aspects. One of them was that the environment that you used to that was used to interact with HyperCard applications was the same as the environment that was used for programming. So you opened your stack of cards, and in one mode you were using it and sort of playing a game or working with your data, but in another mode you could edit the program, add new cards, change the graphics, change the logic. This was one of the things that enabled a lot of people to easily kind of progress from just being a user to being a programmer. And this is an aspect that is sort of completely ignored if we are looking just at the language that was included in this environment to do some programming. So it's really important to look at not just programming languages, but also programming systems. And the big challenge here is that we do not know very well how to study these. What we knew about studying programming systems, we also have partly forgotten. So there's an interesting paper by Dick Gabriel called The Structure of a Programming Language Revolution, where he points out that a lot of the published academic research on programming before the 1990s was thinking more about the entire system, including the sort of running process, running state, including how sort of the state changes in response to some interactions. So a lot of the research was really more about programming systems and not just about the small part of it, which is the language. This is one example why looking at the history of science matters, because there were ways of looking at programming systems that we have sort of forgotten, and if we look at just the language side of things, we are ignoring a lot of interesting aspects. And as Dick Gabriel also points out, even people who try to look at the older papers will often misinterpret them and look at them from the perspective of just kind of the language aspects, ignoring the bigger picture. So one of the motivations for the tiny programming systems is we want to recover the sort of not just the language side, but also the interaction, the working with state. So in the course, we will really look at two different things. We will look at both the programming languages, because there's many interesting things there, but also a little bit at programming systems and interaction. In terms of programming languages, maybe the most basic thing that everyone sort of is interested in is what's the underlying programming language paradigm. Is it imperative programming, where we are writing some statements that mutate the state of the program, change the variables, and so on? Or are we in a functional programming language where there's no mutable state and all the computation happens as a sort of function call that returns a new value? Do we structure the programs as in object-oriented programming, where everything is sort of packaged in an object that hides its own logic and responds to messages? Or do we have some other programming paradigm like logic programming, where we sort of declare facts and then the system behind it, like Prolog, runs some logic to infer answers to our questions from those facts? So those are kind of the basic programming language paradigms, and we will look at some of those. And just to illustrate this, I'll give you a quick example of a little program in Prolog. So what I've got here is a bit of source code that defines in Prolog a couple of entities. So there's a bit of a code that models the British royal family with William, Harry, Charles, and Diana. And then we define some family relationships. So we're saying Diana is a parent of William, Charles is a parent of William, and so on. And then we can define some predicates, like what does it mean in this model to be a father? Well, it means that the person X is a father of person Y if they are parent and if they're also male. And then mother is a parent who's a female. So I can load those facts into my Prolog interpreter in here. And when I load that, Prolog will sort of read through the facts and now we can ask questions. So I can, for example, ask who are the children of Charles? I'm using lowercase for the known primitive entities and uppercase is for variables. And if I do this, then it says, well, one possible assignment for my variable X is William, and another possible assignment is Harry. So one interesting thing here is I actually got multiple answers to my query because there's two possible solutions. I can also ask who's the father of Harry, and this will give me just one answer. You can do more interesting things because the closed world assumption of Prolog means that if I say who are all the fathers in this world, what are their children, then I get one assignment Charles William, another Charles Harry. A more interesting example is the definition at the end here, which is defining how to append lists in Prolog. Lists in Prolog are represented with head and tail, like in functional programming. So you can sort of take the first element and the remainder of a list. And the operation is defined in two using two definitions. One says, if I have an empty list and I want to append x after it, the result is just x. So if I, for example, say append empty list and a list containing 1, 2, 3, then the result is just 1, 2, 3. This call only used this rule. Now the other rule is more interesting. So it says, if I have a list that starts with x and then is followed by y and some other list called z, and appending z after y gives me w, then the overall result is x followed by w. So basically, if I can append the rest of the first list with the second list, then I can also append the whole thing. And this means that I can, for example, say append 1, 2, 3 and 4, 5, 6 and ask for the result. So far, so good. So the interesting thing about Prolog is that it's not really running in the same way as functional programming languages, for example, do, but it's doing a logical inference. And this means that I can, for example, say append x 4, 5, 6 and 2, 3, 4, 5, 6. So if I run this, what will happen? Well, this does have a solution. There's a possible assignment. We can assign 2, 3 to x, and if we do that, then 2, 3 appended with 4, 5, 6 is 2, 3, 4, 5, 6. And there's just one solution there. If I did something that doesn't work, so if I, for example, said, well, is there a solution to appending 4, 5, 6, 7 after something that leads to 4, 5, 6, then the answer is false. There's no solution to that. And I can also use multiple variables here and say, now I'm basically asking Prolog what two lists I can append to get 1, 2, 3, 4, 5, 6. And if I do that, then it will enumerate all the possible options. So it says, well, you could have 1, 2, 3, 4, 5, 6 followed by an empty list, or you can have 1, 2, 3, 4 followed by 5, 6, and so on and so on. So we actually get all possible assignments here. So this is one example where looking at the programming language side is really interesting, because the way Prolog runs is very different than from what you might be used to. The other thing is programming systems. So how you interact with a programming tool or a language. The most common thing that sort of exists around pretty much all programming languages is you can have some sort of command line programming system where you have a code editor. In the code editor, you're editing your program. Then you have some compiler or an interpreter that will take your program, turn it into something you can run. You might have other things like debuggers. So if you're using Visual Studio Code to edit your programs, you're basically in this mode. Our Prolog example is also this kind of interaction. But there's other more interesting things. There's image-based programming model where you have an editor integrated in the programming. You have the editor integrated with the runtime in a way where you always manipulate a running, evolving system. I will show that later on as an example. There's various other things like interactive and live programming systems, where you get some sort of continuous feedback as you're editing code. So you might be sort of changing some parameters, and as you're doing that, the running program updates and starts behaving differently. You can also have interaction where sort of every change, every edit triggers a recomputation, or when new data come in, the state is recomputed. This is, for example, how spreadsheets and Excel work. So I want to show you an example of Smalltalk, and I'm going to be using the emulator for the original Smalltalk implementation, just so that you can sort of see how it actually worked. And the interesting point here is that if you think about Smalltalk, mostly people these days will refer to it as the first object-oriented programming language. And it's really sort of the fact that you have classes and objects that behave in a certain way. But what I think is equally interesting is that Smalltalk is not just the language, but it's the whole environment. So this is a emulator that you can find online that lets you play with Smalltalk. And in the emulator here, what we have is a demo that the Smalltalk research group did for Xerox executives. And you can sort of see some windows that they were already building in the 70s. And the environment is kind of both something intended for end users, as well as something intended for programmers. So the demo that the Smalltalk group did was this little simulation of, well, it was a sort of object-oriented simulation platform that you could use to build all sorts of different simulations. And this was a demo for management, so they built a bunch of simulations around kind of things that people at Xerox were interested in. So I can choose one of the simulations and start it. And now I loaded the simulation, and I can run it, and it's moving copiers and tasks around in the simulation, showing the process and so on. I can similarly load some other simulation and start that, and now it's modeling a different scenario with loading something into trucks. But the interesting thing is, so now I'm interacting with this as an application, as an end user. And if I close the simulation and choose open a browser, then I can create myself a browser. And in browser, you can see all the classes that are defined. So I can, for example, find the classes that represent the factory in the simulation, or I can find a class that represents workers. I can sort of look at their implementation. So, for example, here we have the picture that represents a worker in the simulation, and you can go in this code, change the program live, and if you make a change here, it will immediately affect all the objects that are in your environment. So the really interesting thing here is that Smalltalk is not just the first object-oriented programming language, but it also has a very different kind of perspective on what it means to interact with the programming environment. So that's another thing that is worth thinking about when you're looking at programming systems. And in general, I think what the perspective that we will be following in the course on what really matters about these programming systems is, well, first you have some static structure, that's the program. So some sort of source code that you have at the start. So in the prologue example, that was the source code that I had on one side with my facts. But then we have some dynamic structure or a process that gets created from the static structure. And in all sorts of programming environments, you will end up having some runtime data structures. The static structure of an object-oriented source code is some class definitions. The dynamic structure is then the objects themselves. And for example, in the Smalltalk environment, you can actually explore the dynamic structure, look at the objects while your program is running. And then the interesting thing to talk about is what's the logic of evaluation or the execution. That is, how does the dynamic state evolve as the program runs? So in the case of Smalltalk, you have objects that send messages to other objects, and the internal state of the objects gets updated. In the example of Prolog, you have some substitutions that are constructed and updated as the inference engine is running. And how do you describe these things? Well, in the conventional sort of programming language theory, people write operational semantics. So here's a bunch of rules, for example, that define how a small programming language evaluates. And this works very well on paper, sort of standard way of defining the meaning of programs. What we're going to do in this course is we will write some small interpreters instead of looking at the formal rules. Why write interpreters? Well, one good reason is that interpreters, you can run them and you can see what happens. And also, I'm going to be using the F# programming language, although you're more than welcome to try anything else. But in a language that has functional algebraic data types, it's very, very easy and very, very nice to define the static structure as a data type, the dynamic structure as another data type, and the logic of the evaluation as just a function that transforms the dynamic structure. In the example here, I'm defining types to represent Prolog programs. So a program is just a list of rules. Rule is the head and the body. So what we're kind of deriving from what. And the terms can be atoms like William, variables like X, and a predicate calls with a name of the predicate and a list of arguments. So this is very, very straightforward model of what we had in the programming system.